Alright, so we'll move on to the last part of this section. Again, the opponent will try to learn questions for the course. Number 11, pumpkin straw. Accept it. Okay, so the reporter will prepare a presentation. Yeah, please put down your names. Okay, each presenter on the platform.
presentation from our reporter.
Honorable judges and fellow competitors, I'm the report from Team Excel here, and today I'm going to report about the plumbing straw. First statement, a simple water pump can be made using a straw shaped into a triangle and cut open at the vertices. When such a triangle is partially immersed in water with one of its vertices and rotated around its vertical axis, water may flow up through the straw. Investigate how the geometry and algebraic parameters that will affect the pumping speed. So we will mainly focus on how is the water pumped by spinning straws and random parameters that will affect the pumping speed. And here's the outline. First, for the preliminary experiments, I will demonstrate my observation video, and then to the quantitative theory model, I will use the Bernoulli's principle for my theory. And followed by the experiments, I have done 6 kinds of parameters, and finally is the conclusion. Preliminary experiments and experimental setup and equipment. This is my experimental setup. I fixed the model here. The model is stabilized with a low limit instruction to minimize the vibration. And as the model starts to provide an angle velocity on the straw, the water comes out. After that, the water is gathered by this water and eventually flows through this pipe. At the end of the pipe, a measuring cup is used to collect the water. And also, water may spray on the top, on both sides, on the wall of this container. So I first keep a limited amount of water on the wall, so that although there's water spraying on the wall, there will be some water flowing down the wall. Thus, with this method, the water that needs to be collected will not be absorbed in the wall. And this is the framework of my straw. To increase the variety of my experiments, I choose to 3D print so that the characteristics could reach my expectations. And on the top of this framework is used to connect to the motor, and on the both sides of this framework is used to connect with the straw. And so to let the water flow out, I tighten the board a little so that the water will just flow through this pipe and into the measuring cup. And the way I measure the pumping speed is to record the time it takes for the flow to each 100 milliliters. And each experiment will be done 10 times to reduce errors. And also, to ensure that the amount of water entering the straw remains the same, I have connected external water source and dig a hole here so that the water level won't reduce or increase when the water is spraying out. And phenomenal demonstration, and this is my observation video. As you can see that when the straw is spinning, the water pumps out in tangential direction. And also, small turbulence may form below when the straw is spinning. So I always waited a while till the system reaches stabilized, then I start my data collection. And also we found out that above some angle velocity, the water will almost fill the straw. And here's the quantitative explanation. As the straw starts to spin, since there is a centrifugal force, so that the water pumps out. And let's analyze the forces acting on the water. Since when the straw is rotating, since there is a centrifugal force. However, the water only pumps out when the centrifugal forces component in the direction of the straw is bigger than the gravitational forces in the direction of the straw. The water will pump out. And then I will talk about the quantitative theory model, which I use to develop this principle to calculate my theory. And according to the Bernoulli's principle, the energy of the bottom will equal the energy of the top. And here we consider the dissipative, maybe the energy loss or the friction between the straw and the water, and also some deviations may cause. We have considered it, and also we have considered the viscosity of the water here. And then the continuity of the liquid tells us that the water level will drop by an amount that equal to the water that comes out. So that here we let this as alpha, and then we can find that the velocity of the water flowing in is ignorable, and then the velocity of the water flowing out will be like this. And as you can see in the theory in the formula, the length of the straw, the angle velocity, or the delta, or other parameters, it will affect the flow of velocity, which will affect the pumping rate. An experiment, I have done six kinds of parameters, which will be like the angle velocity, in the distance, straw radius, length of straw, and also the immersion depth. And the first parameter is the included angle, which is here. and it is ranging from 40 to 70 degrees. And for the measurements, I will measure the pumping rate. And for control variables will be the angular velocity that the model gives them, and half in the distance, and straw radius, length of straw, and immersion depth. And as you can see in this chart, the x-axis is the included angle, and the y-axis is the pumping rate. And when the included angle decreases, the radius of the rotation will increase, and also the height that the wire needs to climb will become smaller, which represents that the gravitational potential energy that the wire needs to overcome will become smaller, so that it will be easier for the wire to plunge out. Thus, the pumping rate will increase. And you can see it in this theory too. And this is the theory line that I draw. And since this is only the velocity of the wire, and this is the pumping rate, so we need to let the velocity of the wire flowing out multiple the cross-sectional area, so that it will equal the pumping rate of the theory. And since that I have mentioned that the wire will almost fill the straw, so that the cross-sectional area, we can know the cross-sectional area which will be. And the next parameter is the angular velocity, which is 300, 350, and to 500 rounds per minute. And for measurements will be the pumping rate. And for control variables, will be included angle, after the distance, straw radius, and also the immersion depth. And in this chart, you can see that the x-axis is the angular velocity, and the y-axis is the pumping rate. And when the angular velocity increases, the centimeter of force will become bigger, and it will be easier, and it will be faster. The velocity that the straw brings out water faster, so that the pumping rate will increase. So when the velocity of the water flows out increase, the pumping rate will increase, since that the cross-sectional area remains the same. And also, we also find that if the angular velocity is less than 180 rounds per minute, the water won't come out, which means that they have the boundary limit for the angular velocity. And the third parameter is the half in the distance, which is delta, and it is the delta is here. And to change the delta, we stretch this one. And since I'm using the 3D printer lab, we can easily control the half in the distance. And for the measurements, we also measure the pumping rates. And in this chart, the x-axis is the half in the distance, and the y-axis is the pumping rate. And when the half in this distance increased, since that the radius of the rotation increased, so that it will cause the velocity of the wire flowing out increase, and the pumping rate will thus increase. And here's the theory line. You can see that our experiment data is very fit to our theory line. And then is the straw radius. And since we only could have 0.3 to 0.6 centimeters, so we do two kinds of parameters. And for the other variables will be the control variables, and we'll also measure the pumping rates. And you can see that when the straw radius increases, since that the cross-sectional area will increase, so that the pumping rate will increase. And however, the velocity of the water flowing out will increase. You can see in this theory, which is because that the radius of rotation will increase when the radius of the straw increase. And we think that when the straw radius increase, the pumping rate will increase, which is mainly because cross-sectional area increase. And next parameter is the length of the straw, which is 7, 8, 9, 10, 11, 12, and 13 centimeters. And here is the length of the straw. And for the measurements, we measure the pumping rates. And in this chart, the x-axis is the length of the straw, and the y-axis is the pumping rate. And when the length of the straw increases, the radius of rotation will increase. So it will cause the pumping rate increase. And you can see that when the length of the straw increases, you can see the theory, the velocity of the water flowing out increase. And here's the theory line. And you can see that there is maybe some deviation. And we think that it is mainly caused by the curvature of the wire. Since that when the pumping rate increases, the pumping rate, the curvature of the wire will get stronger, so it causes the experimental error to increase. And next is the immersion depth, which will be 1, 2.5, and 4 centimeters. And for the measurements, we'll also measure the pumping rate. And here are the control variables. And let's chart the x-axis is the immersion depth, and the y-axis is the pumping rate. When the immersion depth increases, we found that the pumping rate won't increase that significantly. They will have only a slight increase. So it means that if the straw is connected with the water, the water will pump out, and it won't change the pumping rate so significant or so obvious. And this appears in the theory too. And here's the conclusion. Why does the water pump out? Since the straw is rotating, so they will have a centrifugal force. However, the water only pumps out when the centrifugal force component in the direction of the straw is bigger than the gravitational forces in the direction of the straw. The water will pump out. And the second conclusion is that the parameters that will affect the pumping rate. And we have the 6 kinds of parameters, and we all measure the pumping rate. And so this is the chart that we'll make. And the x-axis will be the parameter, and the y-axis will be the pumping rate. And the parameters that will possibly correlated with the pumping rate will be the length of the straw, angular velocity, having distance, immersion depth. And for rate, and also the rate of the straw. And the parameters that will negatively correlated with the pumping rate will be the included angle. And we all have the theory line, which is drawn by the velocity of the water flowing out, and we know his cross-sectional area, so we can draw the theory line. And that's my report. Thank you.
Okay, questions from the
Okay, so because the purpose there said that you need to investigate the pumping speed, and how did you define the pumping speed?
I defined the pumping speed as the pumping rate.
Is that the pumping amount per second?
Yeah, the pumping amount.
Okay, and did you think the capillary action will affect the experimental result?
Pardon?
Capillary action.
I think it won't.
It will affect the result. Okay, and next, did you consider the viscous force of the water?
Viscosity of the water. Yes. In my previous theory part, I mentioned that we have in our balance principle we have minus this one, and with this one we have considered the viscosity of the water.
Okay, and did you think that the pumping rate will become faster or slower?
When the viscosity of the water increases, the pumping rate will decrease.
Decrease.
And this is the relationship between them.
And next, because the straws were rotating, right? So did you consider a correlative force?
Correlative force with what do you mean?
Okay, and we can discuss in the discussion time. Okay, and next, did you think if the water level in the container is lower than the straws in that part, and the straws keep rotating, it can pump out the water or not?
You mean the water level will increase or decrease when the water is pumped?
No, I mean the water level is lower than the straws in that part. It means it is lower than this part.
Then you mean the straw didn't contact with the any water, and then the water won't pump out since it doesn't.
So the thinking won't come
I
out.
think it won't. If the water doesn't contact with the straw, it won't.
Okay, and next, I want to ask, did you calculate the pressure in different positions in the straw?
Yes, I have two. I have considered the pressure of the top and the pressure of the bottom here. And here's the pressure here and the pressure here.
So the pressure of the inlet part is bigger than the outlet.
Okay.
And this is bigger and this is small.
Sorry.
Okay.
So preparation of the component.
The topic of my approach today is problem number 11, pumping stroke. And here is the problem statement. And we will mainly focus on which theory is the main effect of the pumping speed and our resistance in this system. And here is overview of the report. From the theoretical model, they use the Bernoulli's principles and the force analysis about the centrifugal force. And they use a lot of formula to fix the Bernoulli's principle, which is just can use in the ideal situation. The pros, they clear force analysis and demonstrate good model. But the cons they didn't consider about the vortex, which will form when the straw is rotated, and didn't consider the Coriolis force. And from the experimental and setup, they changed the inductive, included angle and the angular velocity and the half inlet distance and the straw radius and the length of the straw immersed depth. And the pros, they have the accurate measurement of the pumping water amounts and the lots of experiments are conducted. And the cons, they didn't consider about the effect of the airflow, which the water level is lower than the inlet part. And didn't consider that the whole inlet will also change the included angle. And the data analysis, they compare their parameters with the pumping rate. Okay, and the pros, they compare theoretical and the experimental data, and the cons relate of the straw radius data, and didn't explain why immersion that the value of it is not on the theoretical line. And here is my discussing points, and I want to discuss about the nuclear action. It will affect the result or not, and if they consider viscous force, and the viscous force plays what kind of roles to let the pumping speed become faster or slower. And the experiment is set up, we want to discuss about when the water level lower than the container, then the straws in that part and the straw it can pump out the water or not. And we want to discuss about if they calculate the different position of the pressure in the straw. And the data analysis, we want to discuss about the define of the pumping speed and how will the parameters affect the result of the experiment. Okay, and now I want to discuss with the from the short question, I also have some questions asking. So I want to ask you, in your experiment plan, the straw start to rotate and the water in the container will form a vortex or not?
It will form a vortex.
And
yes.
And you think that will affect the result or not?
I think the vortex won't change the immersion depth at all, since I have a video. And also, I think if the vortex, the direction of the vortex is the same to the direction of the straw. It will make the velocity of the water flowing into the straw faster. So that thus the velocity of the water flowing out will be faster, since the continuity of liquid tells us that if the water fills all of the straw, the velocity of the water flowing in will be the same to the velocity of the water flowing out. So that
if you change the immersed depth of the straw and the vortex will also change.
Yes, the vortex will be small if the immersion depth is.
And did you consider in your data or?
Yes, we have considered in our theory part, since I have to say that the dissipated from the maybe energy loss.
Okay, and did you think that which the water is pumping out, it will have any other motion except the circular motion?
What do you mean?
Like maybe because the water will pump out, right?
Yes.
And you think that except of the circular motion, you will have like rotational motion or what?
I think the water only. I only observed that the motion of the water only pumps out in the tangential direction. I only observed this kind of phenomenon.
Okay, and next, did you think the pumping situation will always continuous, or it will certain? In certain situations, you will pump out the water and the shape of it will like a droplet. It's not non-continuous.
I think the whole process will be constant. And since I have mentioned that I have done the experiment for 10 times, so every time the experiment, I can see that the experiment data is very similar.
No, I mean that if the rotating speed becomes faster, and you found that the water which is pumping out the shape of it will like a droplet, not is the continuous water column. You mean the shape of this?
Yes.
I
I only observed that when the angular velocity increases, the height that the wire can reach will become bigger, will become longer, and it will be more fierce for the water flow.
So, can you explain why you will have in your experiment when the angular velocity become faster, and you said that the shape of it will become like droplet, or
I didn't say that they will become like a droplet. I said that they will just a water flow.
it will just a water flow?
A turbulent flow.
But
I have calculated my real number, and I found that it is a turbulent flow.
But in your like if this part is like a droplet,
Oh, you mean the this part?
or I think if the rotating speed become faster, maybe the viscous force cannot have enough force to get the water shape. So like
What do you mean that? I think that when the wire is pumping out at the initial place, it will be like a flow, and maybe when the distance is longer, you will observe the droplets of the wire, maybe, but at the initial place here, it will like a flow,
okay.
continuously flow.
Okay, and could you move to the front of the lecture?
Okay, sure.
Could you draw a force analysis and the adjustment?
Okay. And this is the axis. And here, if we maybe analyze the forces here, and here's the centrifugal force.
Yeah.
And here we will have the gravitational forces of the wire. Yes. And also the friction here. The friction here.
And did you consider it?
Yes, we consider it.
Okay.
Is the theory.
Okay. So because we can measure for like this part is the FC sin theta, right?
Yes.
And because the centrifugal force is equal to the m omega first.
Yes.
So did you think that when the omega increase and the pumping speed will always increase or not?
I think when you mean when the angular velocity increase, the pumping rate will increase every time.
Yes.
Oh, I think it will.
It will, but I think if the angular velocity becomes faster and this velocity, because this velocity will also become faster, right? And because the water will look like water column shape, but I think it is because of the water will have a viscous force in it. So it can look like a column. And if the rotating speed is become more faster, and I think this force cannot let the shape of it will like the column will like the droplet. So I think the pumping will like
So, what's your question? You said that it will affect the pumping rate or what
Yes,
the shape
and-
of it?
because the shape of it will like this. So
But the water still comes out, right? So the
yes, but I think because it is like this, so the pumping speed will it might decrease because
well,
it is
here
not continuous.
is the velocity,
Yeah.
and it brings out water faster, right?
Yeah.
And so that the velocity here is faster, right?
Yes.
And then the velocity here is faster. So it brings the velocity.
But
and the water
because
flow
it
goes
is not continuous. If this is continuous and it will always be faster. But because this is not continuous, so I think maybe it will decrease.
So why? So well, what will the water flow? The velocity of the here will increase or decrease? I think the velocity of the water flow into the this is the water flow, and I think the velocity of the water flow in will increase. So that if the water fills all the straw, and since that the continuity of liquid tells us that, and this is the cross-sectional area of the straw,
Yeah.
and it will equal to the velocity multiple the cross-sectional area of the straw.
Okay.
And so that if this increases and this remains the same, and this remains the same too, so that this increases and this will increase.
So in your experiment, that is because you use the Bernoulli's principle, right?
And this is a continuity.
No. I said that in your presentation
Yes.
you use the Bernoulli's principle, and you said that this part pressure is bigger than this part
Yes.
pressure. And did you think why this part pressure will be bigger than this
And
part?
since the pressure here is P2 and the pressure here is P1,
Yeah.
and for the pressure here we also need to consider the T1 equals the upper pressure and the water gives the pressure. So we'll need to consider the pressure up here and pressure below.
But I think it's because this straw will rotate, right?
Yes.
And this is the container. And because it will let the water also rotate, and because it will have a rotating speed, so it will let this center part of the water velocity will become faster, I think. And if the water velocity become faster, and the pressure will become small, right?
You mean this pressure here will become small?
No. I mean, if this is rotating, and it will let this part, the pressure of it will become smaller, and the outside of the container water you will want to move to the center.
Yes.
And when it moves to the center, it will let this part water will become bigger. And I think that is why this part pressure of it will become bigger.
Okay.
And did you agree with me?
So you see that the pressure here and the pressure over this one is bigger.
This one is bigger, but it is because
Yes, I agree that the pressure here is bigger.
Yes.
Like I mentioned, I agree that the pressure here is bigger.
Okay, and I asked you if the water level is lower than the stroke in the part, you can come back the water on the upper end.
And what do you mean that? Can you draw me the image?
And this is your stroke, and it does not touch the water surface.
I think if there is no vortex below here, the water level remains the same, right?
Yes.
If there is no vortex or perturbation of the water, the water didn't contact with the straw. The water will come down. But however, if there is maybe a vortex here, the straw contact with the water will climb up the straw and then flow to this part.
Okay, and I think that is not because of the vortex. Because vortex it will form by the stroke in the water, it will form the vortex. But this situation it is not in the water. So I think that is because the stroke will rotate and you will get this part here, you will distance.
But the water needs to overcome its gravitational positional energy. And how do you?
I think I placed the name top, and because it's still rotating, right? So it will let the air flow here become faster, and the pressure of it will become smaller. And it becomes smaller, and the water will want to move to here, and if the water shape of it looks like this one, and touch to the stroke, and can pop out the water.
However, I think that the water will come down. It depends on the distance here, right?
Yes.
Building on your mention, I think it needs to be considered the distance here. If there may be a distance very small, I think
It
yes.
will have a limit, so I think maybe you can.
But I think it will have limits.
Yes. Okay. And so in your experiment, can you give me a short question? How would the geometry affect the experimental results?
And for geometry, we have this include the angle, and here's the theta. And if we control the length of the straw remains the same, then that's what the included angle increase. Right? This is bigger included angle. Since that the gravitational forces, or you can say the height that one climb will become small, or the gravitational forces that need to overcome will become
So you
bigger.
think that is because the
They will be harder.
gravity component for
We can have many explanations for this. First, I will explain that it is because the gravitational forces of potential energy that the water needs to overcome will become bigger, and also the height that the water
Time
needs
is
to
up.
become bigger.
The opponent will summarize the discussion.
Okay, to summarize the discussion. From the theoretical part, we discussed about the effect of the vortex, and the reporter thinks that if the vortex from the pumping state become faster, and I agree with the reporter. And from the first analysis of the water pumping out, we both are thinking if the FC cosine theta is bigger than the gravity components, and it can let the water pumping out. And the pressure difference of the water in the stroke, it can I think the pressure in the inlet curve will become bigger is because of the secondary airflow moves to the center, and then the pressure of it become bigger. So And next, the water pump out will be water droplet or not.
Okay, time is up.
Okay.
Questions from the reviewer?
Thank you for the report and the opponent. And I'm going to ask the report, will the centrifugal force increase or decrease due to the motion that the water is going out?
And what do you mean the motion? The velocity of the water goes up. So
I mean,
do you mean that when I change the parameters or only at the same control variables? Then
it is in control variables that if you pumps out the water is from close to the water and is close to the center and goes to out, right? And the rotation distance will be bigger and will
so you mean that when the radius of rotation will be bigger and the centrifugal force will be bigger if the radius will be bigger?
Okay. And do you think that other geometry shape like square or other shape will occur the same?
I think if this is the, maybe you can say that include angle is 90 degrees or that the straw is vertical. I think that the water won't come down since that the centrifugal forces and while the direction of the water flows is 90 degrees, so that it won't have any work on the water, the centrifugal force.
I think if the shape of it is a square, and I think it won't pump out the water because it will not have the centrifugal force component force to let it out.
Thank you. And will the time that the water, you can say that will fill the whole straw, right?
Almost fill it.
Almost fills, okay. Will the time that change due to different parameters?
And in our variance, we all observe that the water will fill almost fill the straw in our variance. But maybe in a low angle velocity, the water won't fill all of the straw.
Well, the fill time change.
Fill time would be.
The time to almost fill that until it pops out.
We didn't measure it, but we only observed that the filling motion, the filling time is very fast.
And could you explain your
The time that starting to rotate until the water pumps out will it change due to other parameters?
and the question of the what?
The time will change.
The time will change.
The time to
You
fill
think
the straw.
the time. I think if the because I think if the angle velocity becomes bigger and the shape of it will like the droplet. So I think it will not the time of it cannot be too late.
Okay, time is up. Preparation of the reviewer. presentation of the reviewer.
I'm a reviewer from Team Residence, and here's the problem statement. A small water pump can be made using a straw shaped triangle in 1936. When such a triangle is partially immersed in water with one of its vertices and rotated around its cylindrical axis, water may flow up through the straw. Investigate how geometry and other relevant parameters affect the pump speed. And the theory that the water uses is the Bernoulli's principle, and his experiment setup included a motor and a container of its immersed length. And the method used is an included angular velocity, straw radius, length of the straw, and the immersed depth. And to summarize, the strength that we reported is has a complete quantitative phenomenon explanation and allows the experiment to prove the assumption, and has a good experiment setup and good error analysis. Suggestion and lacks simple explanations of the phenomenon. And the opponent, she asked precise question and great discussion. She's well understanding of the reporter's report, and he asked very much details. But I think that she wasted much time answering a single question. In the discussion, the opponent asked whether the water that comes out had downward motion. The reporter only said that he worked on his report, he didn't investigate that, and I think that it will have downward motion, just as the rotation or something. And the opponent asked, will the water come out be like droplets? And the reporter answered that it will be a flow. But I think that as the angular velocity as big as a point, that it will be a droplet. And the opponent asked if the straw doesn't have water, will come out. The reporter says no, but I think that it depends on the distance between the straw and the water. And I asked, the filling time will be changed due to the other parameters. The reporter only that answered that it is fast and he didn't measure it. And I asked when the centrifugal force changes due to the radius that the straw changes. And the reporter answer is yes. And I asked the geometry part. If the shape that straw changes, will it still comes out? And both opponent and reporter says no. Here's our report. I review.
Concluding remarks from the report.
And thanks for the reviewer. And here's the concluding remark. When the angular velocity increases, the pumping rates will increase. And I think the report thinks that angular velocity won't have a boundary limit. But if the angular velocity is very high, I think that the velocity will increase as well. And then the continuity will fit our theory model, which means that the amount of water that flows into the pipe will be the same to that the water flows out. And that the immersion depth is related to the vortex, and also that the opponent just mentioned the pressure difference. And if the straw is vertical, since there is no centrifugal forces component in the direction of, there is no centrifugal forces acting on the water, so that it won't flow out. And then the vortex formed on the water will not affect the result significantly. We have observed that the vortex is very small, and however, the vortex will make the pumping rate bigger, since that it will make the velocity of the water flowing stronger. And then in our experiments, for the 6 parameters, including angle, length of straw, radius of straw, we all find that the water will fill the straw. And also, we have considered the friction and viscosity in the theory. And also some deviation will consider in the theory here. And then we have calculation of the pressure difference for the pressure here and the pressure here. And here's the parameters that will affect the pumping rate will be like this. And just like I mentioned, the water will almost fill the straw, so we can have a theory line. And for deviation explanation, I think the vortex that form on the wire. And thank you.
Questions from the jury? For the leader.
You consider the angle dependence of the pumping rate, right?
Yes.
And this result is depend based on the complicated equation, Bernoulli equation. And can you considering from angle momentum whether this result is
Oh,
reasonable?
you mean that did I consider the angular momentum?
Yeah, from the angle momentum point of view. Can you expect this result is reasonable or not?
I didn't consider the angular momentum.
Actually, this is okay. So.
Oh, you mean I have considered the angular momentum in my theory? Oh, I did have considered it in theory, but since the theory, the whole formula of the equation is so long, so I didn't put it on the report.
You mean that if change the angle of it and you will have to affect the result?
Just the angle theta. So when the theta lower, the smaller, means the angle momentum will large, right? So small angle will induce the pumping rate.
I think,
This result.
but I think it's because if the theta angle becomes smaller and if they control the immersed height of the straw and the water resistance, it will also become smaller because if the theta angle becomes smaller and the immersed area in the water will also become smaller and the water resistance will become smaller, and I think that will affect the angular velocity and affect the pumping speed.
I think that if the angle decreases, that will cause a bit of force to pump the water out. So I think that the pump speed will be bigger.
Any other questions? Professor Chen?
Thank you. So, could you go to the data on page 60?
16?
60, yes. So, although the data and the experiment, they have some correlation, but the curvatures are quite different. So, do you think your theory can explain your data well or fully?
What do you mean for the last two?
Yeah, I want to ask your opinion whether you think your theory explain the experimental observation accurately or fully.
I think my theory can expand my experimental data, and it also fits to our experimental data well. Thank you.
Okay, thank you. So how about your opinions when you compare the experimental data and the theory?
We can see that when the angular velocity becomes bigger and the pumping speed will a little bit bigger than the theoretical line. And I think that is because it is because the vortex and the vortex of the water maybe will let the pumping rate become faster.
Should I answer?
Yeah, please.
I think that his theory and his experiment, maybe there are some problems between the factors that he considered. Maybe there's something missing that his experiment didn't fit his theory well. I think that it should be fixed. Should be remade the theory.
Any other questions? Also, then, can I ask a question for the opponent? Yeah. So under what conditions you think you can actually pump out discrete droplets? Because I think that's the question you asked.
I think it is that if the angular velocity become more bigger, and and more bigger. And because if the water pumping out, the shape of it is like a droplet, I think it is because the viscous force of the water, it cannot get the shape of it like a water column. It is because the angular velocity is become much bigger, and the force of the pumping out become much bigger. So the force of the viscosity, and it cannot let the water shape like a column.
So have you really done that? Perform the experiment?
Because I'm the opponent, so I can't down the.
You've done that before. You have done that before, or no? No, I mean, have you tried this experiment before?
Yes, I have tried this.
Okay, thank you. Okay, have to see. Right, so that's a score count. The scores for the reporter. Nine, 8, 8, 8, and 8. Very good. Scores for the opponent. 8, 8, 8, 5, and 8. Scores for the reviewer. 7, 8, 7, 4, and 6. Okay. Thank you very much. Okay, so